Swayam Prabha. Digital India. Educated India.
So far we have been talking about the kinetics of single substrate enzyme catalyzed reactions, and as we all know that in the living cells a large variety of enzymes interact with the multiple substrates. In fact, most of the enzyme catalyzed reactions that do take place in a living cell involve two substrates in most cases, and we have also seen that under certain set of conditions the classical Michaelis-Menten kinetics, which has been proposed for single substrate enzymatic reactions, can also be applied to bisubstrate reactions. Of course, certain conditions apply, but those conditions are by and large extreme conditions, that is, you have to have one of the substrate in a very large excess concentration. Now, those situations may not really exist in a living cell. In a living cell, the concentration of the two substrates that are to interact with the enzyme may be almost in a equal or neighboring concentration levels. They may not be extremely different, and therefore, it is necessary to look at the actual effect of the bisubstrate reactions on the reaction rate. Now, two of the examples which I have chosen here are one on alcohol dehydrogenase, which oxidizes ethanol to acetaldehyde involving a coenzyme NAD, and the other is hexokinase catalyzed phosphorylation of glucose or any other hexose to the corresponding phosphorylated sugar. Now, as a matter of fact, if you look at bulk of the bisubstrate reactions do fall in the category of either oxidoreductases or transferases or ligases. Most of the hydrolytic enzymes, isomerases, are often can be analyzed using classical Michaelis-Menten kinetics. The oxidoreductase represented by the first reaction, or a transferase represented by hexokinase, or in many cases ligases, are the real true bisubstrate reactions which in general should not be treated or analyzed with the Michaelis-Menten kinetics. Now, to account for the rate of reaction for such reactions, taking example of a typical bisubstrate reaction as I have shown here in general. Now, we must I have left certain dots in between the substrate as well as the product stream. Basically, that signifies that the interaction, the dynamics of the interaction between the enzyme and the substrate molecule may be quite varied, unlike in the case of a Michaelis-Menten kinetics, where you have a single substrate, it has to bind on the bindings on the active sites of the enzyme molecule and form an enzyme substrate complex. Now, we are here because the substrates are more than one, there are many possibilities for interaction between the substrate and the enzyme molecule, and so therefore, these dotted figures indicate a variety of interactions that are involved. But in general, the action of enzymes on a reaction involving two substrates A and B giving rise to products X and Y is expressed here. Now, a very generalized rate expression for this was proposed by Alberti based on a steady state hypothesis. I mean again the similar considerations as we talked about in the case of Michaelis-Menten kinetics. He proposed the initial reaction rate for such a reaction can be given by an expression given here. Let us say this is expression 1, that is V naught is equal to Vm into A into B. Bm is the maximum reaction velocity where both the substrates A and B are in saturating concentrations. That means both the substrates are in large quantity and they are able to saturate the enzyme, which is in concentration terms is much smaller than the A or B. The concentration of enzyme essentially is much smaller than either A or B, almost the same assumption that we made in case of Michaelis-Menten kinetics, and the A and B can reach to a saturating level, provide a maximum reaction velocity, and the denominator term gives you another 3 parameters, another 3 kinetic parameters. K dash A essentially is the dissociation constant of binding of E to A, EA. So, mind it that this is essentially a dissociation constant. Now, and Kb and Ka indicated here are essentially the concentration of substrates, concentration of the substrates A and B respectively, at which the reaction velocity is half the maximum reaction velocity at saturating level of the other substrate. That means, when we talk of Kb, Kb is that concentration of B at which the reaction velocity V is half of that of Bm at a saturating concentration of A. Similarly, for Ka, that concentration of A at which the reaction velocity is half that of Vm at a saturating concentration of B. Now, I think so, or in other words, they are analogous to our classical Michaelis-Menten constant for the substrate. That means, you can consider that essentially Kb is the Michaelis-Menten constant with respect to B at saturating concentration of A, and same analogous is the. Now, there might be some confusion about Ka and K dash A. K dash A is the dissociation constant for binding of A to the enzyme. Ka is the corresponding Michaelis-Menten constant with respect to A. Now, the distinction between the two will be more clarified or clear when we proceed ahead, but such a situation exists in the case of bi-substrate reactions. In most cases, that this dissociation constant is different than the apparent Michaelis-Menten constant, unlike in the case of single substrate reaction where their two are almost identical, because you will notice that the apparent Michaelis-Menten constant will depend upon the concentration of the other substrate also, and this dissociation does not depend upon the other substrate. And of course, in one of the mechanisms, as we talked, out of the several mechanisms, in one of the mechanisms, this K dash A may equal to Ka, and the rate expression will accordingly get modified. And under those conditions, you will notice that if you take the expression first in general, you will notice that this can also be considered almost like a, as we mentioned earlier while looking at the validity of Michaelis-Menten kinetics for bi-substrate reactions, that if we put one of the substrate concentration in excess, the expression can represent the bi-substrate reaction kinetically with respect to the other substrate. So, therefore, if you put, let us say if let us say if B is very large, B tend to infinity, then V naught will become equal to Vm into A upon Km plus A, both from numerator and denominator you divide by B, you will end up, some of the terms will be cancelled, and you will end up a simple expression which is essentially like a Michaelis-Menten. Similarly, when A tend to infinity, analogous expression will emerge, Vm into V upon Km, or so rather I would say this will be Ka and Kb plus B, not Km. Okay. So, you get a similar expression in the case of excess concentration of or large concentration of one of the reactant, and that was also the understanding we had when we discussed Michaelis-Menten kinetics. Now you can also look at, you can rearrange this general expression what we I talked earlier by taking certain factors and divide both, and you can end up at a constant concentration of B. If you consider, let us say, B as a constant at some value of B, the expression will turn out to be analogous to Michaelis-Menten constant, Vm into A into B upon. So, if this becomes a constant parameter, you will end up in a term at constant B. You can write V naught equal to Vm into A into B upon Kb plus B whole divided by K dash A into Kb plus Ka into B, this whole divided by Kb plus B plus A. Now this is essentially we have rearranged the general equation in the form of Michaelis-Menten expression. So therefore, at any constant value of B, you can consider that the apparent value of Ka, the apparent value of Km for A, Ka is your K dash A, Kb plus Ka into B upon Kb plus B. So this is essentially the apparent Km with respect to A, I mean by rearranging our general equation. So therefore, essentially you notice that our K, now you can realize the relationship between the apparent Km for A and Ka dash. I mean, although they are related, but it also involves the concentration term of the other substrate, which is B, and a similar relationship will exist when you consider constant concentration of A and the apparent Km for B. Now, or in other words, if you also consider that, if you also go further and if you say that when K dash A becomes equal to Ka, in a very special case, when K dash A becomes Ka, your Ka apparent will essentially become independent of B, will become equal to Kb. The Km apparent will become equal to Kb, and it will be independent of B. Therefore, essentially the relationship between these two terms essentially applies that when they are same as the Michaelis-Menten constant with respect to A, it does not interfere, or when Ka dash becomes equal to Ka, it has no effect on the binding of B. So it is independent of concentration of B in the reaction mixture. And similar situation will apply when if you consider Km apparent for B will be equal to your K dash A Kb plus Kb into A upon Ka plus A. And again here also similarly you will notice that at K dash A equal to Ka, you will have Km apparent for B will be your Kb. Yes. Pardon? Pardon?
K prime is equal to K again, or should it be Kb?
Sorry. No, this is here also K prime A is equal to Ka. It is with respect to only the first substrate binding. Yes.
So is K A dash equal to K is an assumption?
Under this condition, no, this is just I am trying to give you a analogy or an explanation how are Ka and K dash A related. You see, if you consider the single substrate reaction, the dissociation constant of substrate with the enzyme is analogous to Km value. Now, whereas in the case of a bisubstrate reaction, that situation is not true. That is only a special case of a bisubstrate reaction, under which the Km apparent for B will become equal to Kb when these two become equal. Otherwise the value will be this magnitude, although they will have relationship, but they will be a function of other substrate concentration. The other substrate concentration will influence the magnitude of Km apparent in the case of a bisubstrate reaction, whereas in the case of a single substrate reaction the Km value was almost analogous, of course under the assumption that the turnover number, that is K2 term, is not very small. That was the only assumption. Otherwise if it is very small, yes, they have a difference, but if it is not very small, the two are analogous. So basically the Ka and
So in
yes.
the first case, the Km apparent is equal to Kb.
It should be K.
Ka.
K.
Pardon?
In the first case,
yes, you are right.
K.
This should be Ka, you are right. Now you can also look at these expressions in a graphical mode and to have a better visualization. Now in the first case, when we are talking of constant B, your profile will be something like this. This is your maximum reaction velocity and your half Vm will be this one, where Ka apparent will be equal to the Km value for the with respect to substrate A apparently will be K dash A Kb plus Ka into B upon Kb plus B, and similarly here this situation will come of V0 when the value of B is saturating. It will be Vm when the value of B is saturating. At any other B value of B, the rate profile will be a hyperbolic profile analogous to that of Michaelis-Menten constant. Similarly, in the case of A constant, you will have another Km value, Km apparent will be equal to K dash A Kb plus Kb into A upon Ka plus A, and essentially here also this is your constant A. This will be the maximum reaction velocity when A becomes saturating, and such a situation can be conceived as a simplification of Michaelis-Menten system. Now another way to look at yeah effective meetings. Another way to look at these kinetic expression is just like we have been looking under all the cases of single substrate reaction, double reciprocal plots, because they will also give us, as a matter of fact, the magnitude of all the kinetic parameter that are involved. Now what will be the kind of a double reciprocal plot in the case of a generalized rate expression? One can just write 1 upon V naught equal to 1 plus Ka upon A plus Kb upon V plus K dash A Kb upon Av, this whole divided by Vm. Now that is a double reciprocal plot. If you divide both numerator and denominator by A into B, you will get such expression. Now here if you plot this and say for example at a constant value of B, just like in the first case when we take a constant value of B, and you will get a profile with B increasing at different constant values of V. If B increases, you will get a slope of Ka plus Ka dash Kb upon Kb upon Vm, sorry, Ka plus Ka dash Kb upon V, Kb, this will be upon B upon Vm, and the intercept on this factor will be 1 plus Kb upon B upon Vm. So, you will notice that both slope and intercept will decrease, slope as well as intercept of the profiles will decrease as you increase the value of B, and ultimately you will end up, when this B becomes saturating, it almost comes to a Michaelis-Menten, it will be a typical Ka value for the substrate A. And now from the essentially experimentally, to determine the magnitudes of Ka, Kb, Ka dash and Vm can be determined by analysis, by double reciprocal plot analysis, as we saw. Now, essentially just like when we, if you recall what we did in the case of the inhibition patterns, that we took the double reciprocal plots and then took slopes and intercept and made secondary plot. Similarly, here can be done, that if you plot your 1 upon V versus say slope, the magnitude of slope, you will get again a straight line with a slope equal to Ka dash Kb over Vm and intercept of Ka upon Vm. In the case of intercept, the slope will be Kb upon Vm and intercept of 1 upon Vm. So, therefore, by a double reciprocal plot at different concentrations of B and plotting again the 1 upon B versus the slope and intercept, one can determine the values of the 4 parameters, kinetic parameters that are involved in a bi-substrate reaction, that is Ka, Kb, Ka dash, Kb and Vm. Essentially these are the 4 kinetic parameters, unlike in the case of a single substrate reaction where we are concerned only with 2 kinetic parameters, Km and Bm. So, one can determine experimentally the various various kinetic parameters in the case of a bi-substrate reaction. Now, I think you will notice that while looking at the generalized expression of the bi-substrate reactions rate expression, we have assumed that we have not really bothered about the dynamics of enzyme substrate interaction. We have just kept it a black box. Some interaction takes place by which the products are formed, and some general rate expression have been arrived at, which involves certain kinetic parameters which have been considered an analogy to single substrate reactions, because the kinetic analysis of enzyme catalyzed reactions have been so much dominated by the Michaelis-Menten kinetics that any new mechanism or any proposed mechanism must be interpreted in the light of those Km and Vm as parameters, and that is what we have done. Now, essentially we must also look at that what are the possible kind of interactions that are likely to take place, and of course, almost all the interactions between enzyme and substrate for bi-substrate reaction have been classified into some general forms. The first form, the first complex formation can be considered as the random ternary complex formation. I think when we are talking of enzyme and 2 substrates, there is quite a logical choice that we might end up, instead of a binary complex, a ternary complex. That means where E, A and B, all the 3 are combined together before a product formation takes place. Mind it that when I talk of ternary complex formation, I am referring to a ternary complex formation before the product is formed, and in the case of a random ternary complex formation, the enzyme can form binary complexes EA and EB to start with, and also the ternary complex EAB with no restriction on the order in which A and B bind to the enzyme. I mean, it can start by binding first with A and then B will hook on to that, or it can start with EB and then A will hook on to that, and or in other words, as you will notice that just like in the case of a non-competitive inhibition, the A and B both have separate binding sites on the enzyme molecule, and therefore they do not interfere with each other, and randomly they can bind and result, and once the ternary complex formation has taken place, the product formation will begin. Now, essentially you can express it in a mechanistic way, the enzyme going to EA or EB and essentially again EAB and so obviously I mean these four, this will can in a cyclic form and the EAB then goes to form your E plus X plus bi, and of course there will be rate constant at each stage K1, K minus 1, K2, K minus 2, K3, K minus 3, K4, K minus 4. Now, basically the what is either reaction can go in this direction or in this direction, there is no constraint on the order of the ternary complex formation, and such a system essentially is a typical examples in the enzymes are either yeast alcohol dehydrogenase follows such a kind of mechanism. When it now you will notice another typical feature that when we say that the kinetic parameters of the same enzyme which catalyzes the same reaction from two different sources are different, and you will notice that for example yeast alcohol dehydrogenase follows a random ternary complex formation in product form in the I mean as a part of the dynamics of their enzyme substrate interaction, whereas the same enzyme alcohol dehydrogenase from mammalian cells forms does not follow this kind of a mechanism, it follows an ordered mechanism where it can bind only to one of the substrate first before the second substrate can bind, and that is why the kinetic parameters will automatically turn out to be different. One of the reasons in such cases is based on the different reaction mechanisms that are involved. Similarly, yeast hexokinase also follows this kind of mechanism where the ternary complex formation is obtained. Yes.
So why is K4 not equal to K2?
K4 not
Equal to K2 if they are not interfering with each other, A and B binding of A and B.
right.
So K4 should be equal to K2.
They may or they may not be. They may be equal to in some cases, or they may not be equal to, because ultimately the multiplication of the two dissociation constant in reaching to EAB will be same. Now they may or may not be equal to. In some cases, yes, as a specific case, it could be equal to also, but we have just put the different rate constants. The second case again with respect to ternary complex formation is ordered ternary complex formation. Here the ternary complex EAB can be formed from only one of the complex EA, I mean just I have taken hypothetically EA, it could be EB also, and only one of the binary complex has to trigger the enzyme substrate interaction, and then the other substrate will interact with the EA complex to form. That means essentially, in other words, if you write down the reaction mechanism, EA, this is K1, K minus 1, and then this will go to EAB, K2, K minus 2. Now obviously the reaction in this direction B cannot bind to the E, free E, and essentially the reaction has to proceed in a anti-clockwise fashion. That means after E has bound to E, B will bound to EA, EAB will be formed, and ultimately this will form you E by releasing one of the product, let us say X, and then this will release another product by, and they will be, let us say K3, K4. But the product formation will take place only after the ternary complex formation has begun. The process in this direction is not feasible. Now the ordered ternary complex formation, as I mentioned, is a typical example is your liver alcohol dehydrogenase, which is obtained in the mammalian from mammalian systems, and also lactate dehydrogenase is another example of ordered ternary complex formation. And you can see that the same alcohol dehydrogenase can follow different mechanisms, and that is the. Now, a special case of ordered ternary complex formation is Thorel and Chance mechanism, because in many of the enzyme catalyzed reactions, Thorel and Chance observed that very often the ternary complex is not a very stable entity, and it exists only for a short period of time. A special case of ordered ternary complex formation when B reacts with EA, of course, the order is important. B can only react with enzyme only when A has bound to it to form, and the one of the product is released and a modified enzyme substrate complex is generated. That means, a modified enzyme substrate complex is generated and a first product has been released without the formation of a stable ternary complex of kinetic significance. That means, the half life of the ternary complex is very, very small in this case, although they never defined, they never said that the ternary complex formation does not take place. They agreed that ternary complex formation is taking place, but the half life of the ternary complex is essentially very small, and before that the second reaction, the second substrate can interact with the EA to form the first product, or in other words you can have E again going to EA, and then this EA can then convert into EY releasing a product X, and then this EY can give you back EA releasing the product another product Y, and you can have K1, K minus 1, K2, K3, and such a kind of a system where although the second substrate B reacts with the EA to give you the first product, and the ternary complex is not a very stable entity, is classified into the Thorel and Chance mechanism. A typical example of such a reaction is glyceraldehyde 3-phosphate dehydrogenase, which you also come across in the case of glycolysis. So, that is but it is only a special case of a ordered mechanism, where ordered one is ternary complex formation is not denied. We still it is not, one can also consider it either as a special case of ternary complex formation or a special case of binary complex formation. That means, but binary complex cannot lead to a product. Yeah, the third the second substrate has to interact with the binary complex before the first product can arrive at, but the stable intermediates are only EA and EY. The fourth mechanism, which essentially represents the binary complex formation, essentially is ping pong mechanism. You will also notice in many books as written as ping pong bi-bi mechanism. Now, the term bi-bi refers to substrate and product. Bi-bi refers to bi means two substrates and two products. Now, in case of many of the ligases, the situation may be bi-uni, that means the product may be 1 and substrates may be 2. So, all those cases are clubbed under ping pong mechanism, and in this case of ping pong mechanism, the basic hypothesis is that the no ternary complex is formed. As soon as the first substrate binds to the enzyme, it can react to form the B to form a product, or it can split off to a product E. Something similar, you will notice that the two things like Thorel and Chance mechanism and the ping pong mechanism in some way might show analogy. That means, as soon as the EA of the first binary complex is formed, the attack or the interaction with the second substrate forms a product, first product, or it splits off to a product and a modified enzyme substrate complex, which then reacts with the B to form bi, and therefore, your EA this is, let us say, K1, K minus 1 will now, right at this stage itself the product will be formed. sorry X, and this will be your EA dash, and this is K2. Then EA dash then is interacted with B to give you EA dash B, and then this gives you a product again by K3 K4. Now basically the name ping pong is just, as soon as the first binary subject complex is formed, one of the product is released, then the next substrate interacts, the next product is released. So and that is what happens in such cases, and a large number of transferases, most of the bulk of the transferases fall in the category of ping pong reaction mechanism. Excepting those of the yeast source, most of the mammalian hexokinases and all that, they form under the category of ping pong. They lead to the classification of ping pong mechanism. So these are the variety of. Now you will notice that when we look into these mechanisms and develop steady state rate expressions specifically into the, you will end up in quite complex situations.
So, should EA dash B be formed here?
Yes. Now obviously this EA dash essentially is something which is hypothetical in the sense it may not be a binary complex.
Okay.
It is a, or you can write it as E dash. I think it will be better, more clear. It is E dash, a enzyme in the modified form. The first substrate has reacted and released a product. Enzyme is modified. Second substrate attacks, the releases another product. I think that will be a better interpretation. Okay. And whereas in the case of the Thorel chance mechanism, this will be a binary complex. This will not be a modified enzyme. Now, as you will notice that when we look at these reaction mechanisms, with the increased order of complexity between the dynamics of enzyme substrate interaction, the rate expression also will be quite complex if you put them in terms of individual rate constants. As you can notice that each of the reaction mechanism involves, particularly the random ternary complex formation will involve 9 rate constants, 4 reversible and 1 irreversible step, 9 rate constants, and the expression will be quite complex. And I mean in practice to derive expression may be quite complex, and of course we are talking only of binary substrate complex formation. There might be enzymatic reactions which may involve 3 substrates. System will be still more complex. Now I think before I go to the give you the rate expression for these different mechanisms, I would like to introduce you to a simplified methodology for writing a rate expression under steady state hypothesis. Of course the steady state hypothesis is valid. The method was proposed by King and Altman way back in 1956. They gave a method. In fact, they analyzed number of reaction mechanisms, and using matrix algebra they wrote down rate expression for different kinetic mechanisms and proposed a method that okay, you can solve obviously with all use of matrix algebra, all steady state expressions can be solved out. Ultimately making some generalizations from those matrix algebra, Wong and Haynes in 1962 proposed certain set of simplified rules, almost like empirical rules, although they are based on hardcore mathematics, matrix algebra, but he just generalized certain rules so that by observation of the reaction mechanism, as long as you can write a reaction mechanism, one can arrive at a rate expression in a simplistic way. So I will probably try to introduce you with that kind of a system, taking a simple example, so that can be applied to our these complex binary substrate system to arrive at the actual rate expressions. Now the kind of system we will take for simplicity will be a two enzyme substrate complex formation, ES going to ET going to E plus P. We can take a reversible system, K1, K minus 1, K2, K minus 2, K3, K minus 3. So, let us assume, just to illustrate the procedure what they follow, I mean I just choose this reaction mechanism. Now, the very first step in such a reaction, such a procedure as proposed by Bong and Hans is that very first thing is what we need to do is that write any reaction mechanism in a cyclic form. Reaction mechanism in a cyclic form. Cyclic form means you will have interconvergence of the enzyme substrate complexes. Now, for example, here as you notice enzyme species can exist in the form of E, ES and ET in 3 form. So, the whole reaction mechanism can be interpreted in the form of a triangle with 3 vertices, each vertex representing one of the enzyme species. And so, therefore, you can write such a reaction mechanism as E, ES, ET. Now, so the interconversion of each of the enzyme species, say for example, ES, ET, ES to ET, and now let us say this is your S K1, K minus 1. Then, pardon?
So why SK1?
I'll explain that. I'll explain that. Then you have K3, sorry, and K2, and K minus 2, K3, and P into K3, K minus 3. Now, basically, we write the rate constant for all these steps in the cyclic form, assuming or making them in the kind of a first order rate constants. For example, wherever there is a substrate involved in the for example, in a binding of enzyme to substrate, a substrate is involved, the rate constant can be written as S into K1. Where there is no substrate involved, only simple rate constant can be written. And similarly, wherever product is concerned, because ET goes into form the product, in the reverse direction, the product concentration will be incorporated. So, basically, the interconvergence of the enzyme forms involved, each step must be described by a, now these are called kappa terms. The conversion of the rate constant or interpreting each of the step in terms of a first order rate constant term is called, each of these term is called kappa. Now, the next step is,
so is it only valid only if the substrate binds?
yeah, only with the substrate binds, right.
That time
Will come we have for each enzyme species. Now, then we consider each enzyme species in a sequence. For example, we take E and consider all the possible pathways by which E is formed in this cyclic manner. Now, E can be formed by all the possible pathways involving n minus 1 steps. That means, if there are 3 species, there are 3 enzyme species, number of species are n, then n minus 1 steps be involved in each pathway. We identify now for E can be formed by this, for example, this and this. Now, obviously, we can consider similarly you can form this and this, is that right? Write all the possible pathways which are feasible to form a particular, this is for E actually. Now, what I am trying to explain is that for each of the enzyme species, now write down all the pathways which are involving n minus 1 steps. That means, if it is a 3 enzyme species system, if there are 3 enzyme species system, then each pathway must consist of 2 steps which can form the enzyme species E or any enzyme species which we are considering. Now, one of the consideration in such a system is that all the species, all the pathways that converge at this enzyme species, that means like for example systems like this are possible. That means all the pathways which converge at a particular enzyme species are permissible, but no pathway which leaves the enzyme species both directions is not permissible. That means a system like this will not be permissible if it happens. Are you clear? For each of the enzyme species, we work out the pathways by which the species will be synthesized. Each pathway must consist of n minus 1 step, where n is the number of enzyme species present, and the product of the kappas of the steps in each pathway is determined. Now each of you can write the kappas here and you can have the kappa product. For example, what is the kappa product for this pathway? K minus 1 and P K minus 1 K minus 3. This pathway is represented by this and this. So the kappa, the product of this kappa is this. Now in this case it is K minus 2 and K minus 1, K minus 1, K minus 2 for this one, and the third pathway will be your K2 and P K2 K minus 3. Now you will find that similarly you will write down the you see,
Talking only about the formation of the enzyme species.
yeah,
So in that case,
Only
if we
sim-
consider ES, then you are considering by K minus 2 you are forming
K minus
2, you are forming K minus 2 right hand side. K minus 2 is
no, we are talking of E. We are at the, in this expression we are writing for the formation of the enzyme species E.
then what are the second set of arrows and the third set of arrows?
This one,
Yeah, I am talking about those two.
this one. Now these arrows represent your this and this.
So by K minus 1 it should be SK1.
Huh?
SK1 K minus 1.
No, formation will not be SK1 doesn't form E. SK1 form ES.
So, but K minus 2 is also not forming, or
But by ES it will form E. What we mentioned that we are considering only pathways which have 2 steps, n minus 1 steps, and any steps which lead to formation of E involving 2 steps will be considered.
So then the first pathway
one is
does
not
involve
for-
two steps. There are two different.
First pathway involving 2 steps.
Then it should
This one and this one.
So you can't call this a
So
pathway.
these are separate steps.
So these are
They
separate
are
steps.
No.
separate steps.
Not pathway in the term of metabolic pathway that where they are all linked, but these are only the steps which are involved in formation of E, and all steps involving 2. That's what I am saying. They are just generalized rules, and they are not really. Otherwise, you have to go to the matrix algebra to solve the simultaneous equations, and you will arrive at the same thing. What Wong and Haynes did was he simplified the whole matrix algebra, did by King and Altman, and formed certain rules. And he said that you form a cyclic rate expression, cyclic reaction mechanism, and write down the basis pathway for each of the enzyme species. Or for example, we can take even a simpler case. Let us take the classical, the simpler case of E plus S going to ES. Probably which is much more probably the simplest case, E plus P K1. I think try to write this one using the same, you will arrive at the same expression as Michaelis-Menten equation. Of course, for such a simple system, writing by observation will look to be more difficult than solving the steady state equation, but if you have, let us say, more than one enzyme substrate complex, it may look to be simpler to write by observation.
So what is
So I
the
think
n
it is-
minus 1? N represents
N represents the number of enzyme species involved in the mechanism.
that
that-
E, ET, ES all.
Yeah. So whereas in the case of what I showed, we have 3 enzyme species, E, ES and ET. So it will be expressed in the cyclic form by a triangle. Each enzyme species represented on the vertex of a triangle, and each of the pathway which should be considered for formation of the enzyme species must have n minus 1 steps.
First one is not a pathway.
It's not a question of this is not, this is how you define a pathway. It's not a pathway in the sense of metabolic pathway. It's a number of steps involved in formation of that, each having n minus 1 step. So I think we will stop at this point. And